Topic of today's lecture is issues in location of facilities. We are now making a transition from the first major decision in the life cycle of a production system, namely the design of products and services, to the location and layout of facilities. I think at the outset we must understand that decisions of location are strategic. What we mean by strategic decisions is that location decisions are liable to affect the entire organization, unlike a tactical decision which might affect only a portion of the employees in an organization. If you decide to locate the factory at Gurgaon, everyone has to go to Gurgaon, and therefore it's a decision which is affecting the entire organization. Also, location decisions are operative over long time spans, which means that it's not easy to change the decision of location once you have decided to, for instance, locate a plant at Gurgaon. You can't say that day after tomorrow I'm going to change it to Bombay or to Chennai. It's not possible to do that. Whereas this decision therefore will stay with you for a long period of time. And moreover, such decisions are difficult to reverse because the cost involved in reversing the decision is generally enormous. And moreover, all such location decisions are capital intensive. So all these things suggest that location decisions ought to be taken very carefully after consideration of the variety of factors which are relevant for that particular decision. However, it is unfortunate that in many situations decisions of location are based on only a single factor, like free land is available somewhere and therefore the owner is tempted to set up the factory at that particular location, and he might find that he might regret over his decision, because later on he might find that he has to pay continued disbenefits of this particular decision over the entire lifespan. So the point that we are making is that because location decisions are strategic in nature, careful consideration of where to locate the manufacturing plant is actually required. Before we talk about the location of a plant, it would be worthwhile to look at this hierarchy of location problems. For instance, what we find is at the top of the hierarchy we have the location of the manufacturing plant. Now, once you have located the manufacturing plant in some location, what is the next decision? The next decision is to determine the plant layout. That means you are basically talking about the location of departments within the plant that you have decided to locate in the first place. So plant layout is essentially the location of individual departments within the plant location exercise itself. Then when you talk about a department, each department has been located. What do you do next? You talk about physical arrangement of machines and equipment within the department. And once the machines are laid out in the department, the final decision is workplace layout. That means you are trying to find out that if an operator has to work on this particular machine, where should be the location of his tools, where should be the location of the raw materials, how should he make his hand movements and things of that kind. So it's the workplace layout. Do you notice any similarity between these various decisions? In fact, you would notice that all of these are actually location problems. The only thing which changes when you go from one problem to the other is the entity which you are trying to locate. Here the entity is the manufacturing plant itself, and you are trying to locate that. Here the entity is the individual departments which you are trying to locate. Here the entity is the machines and equipment which you are trying to locate. And here it is the tools and the raw materials and the seating space. These are the kinds of things that you are trying to locate. So recognizing this fact, in fact this problem of plant location, which is of strategic importance, the term used these days is facility location rather than plant location. If you took a course on production management, say 10 years ago, you would study things like plant location and layout. But courses nowadays often go by the term facility location rather than plant location. The reason for this is here, because the same kinds of mathematical models and tools can be utilized to handle the variety of facilities. So you are talking about a generalized body of knowledge which deals with the location of facilities in general, and if you define the facility as a manufacturing plant, you are dealing with this problem. If you define the facility as a department, then you are dealing with the plant layout problem. If you define the facility as a machine or an equipment, you are dealing with this problem. And if you define your facility as the tools and the raw materials, you are dealing essentially with this problem. So it is the increased generality of location models and theories which has prompted this change to facility location rather than just plant location. But nevertheless, plant location is a problem of strategic importance, and this is the problem of at the operational level, the tactical level. You can change these layout decisions. It's difficult to change these decisions. So the term facility location, as we have just defined it, emphasizes the generalized approach that handles the variety of the above mentioned problems. So that's why we will be dealing with the facility location problem, and in fact we will be talking about many of the generalized models that are available for dealing with facility location. Another important thing to realize is that location decisions are dynamic decisions, which means that it's not that you take a decision once and there is no further decision to be taken. It's not a one-time decision. Decisions can change, and these changes could be owing to changing technology, the changing nature of competition and different competitors on the scene, change of consumer tastes. All these things in fact force us in making the various decisions about new plants, expansion, decentralization, plant shutdown. All these decisions are constantly going on. The demand is increasing, you have one plant, you might want to expand. So the question is, which plant do you expand out of the existing plants and so on? Which ones do you decentralize? And if demand falls and for various reasons you are shutting down a product, then which plant to shut down? So all these decisions are constantly under review. In fact, we will consider an example where we will see how the dynamic nature of plant location manifests itself in real life decision making. However, before we do that, let's try to identify some of the major factors in location. We are talking here primarily about plant location. So if you are talking about the location of a manufacturing plant, which are the factors which are relevant? Obviously the market is a very important factor, isn't it? How do you think the market would affect the location of a manufacturing plant? yes, that's one thing. Transportation costs and the location of the market would be in fact an important factor, but what is really significant for us is that the plant has to produce something, some products, and these products have to be transported to the market, and therefore in fact in earlier models of transportation, what was felt was that if you find out the distribution of demand spatially, which could occur at different points in space, and if you then calculate a center of market very much like a center of gravity by assuming that the weightage given to individual points is equal to the market demand at that point, then the earlier theories of location said that the center of market is the best place for locating the manufacturing plant. Now, although this was not a wrong argument, but obviously it was an incomplete argument because it was considering only market. The same thing could be true about raw materials, because raw materials are needed for the plant. So the manner in which raw materials are available could affect the location of the manufacturing plant. Let us for instance take an example of how raw materials can affect the plant. Let us say for instance that we could possibly think of three kinds of raw materials. We could think of pure materials, by pure materials we mean those materials which do not lose weight while the process is going on. Let us take for example a simple situation. Let us say for instance that this is the market, and the raw material source is what we call pure materials. Pure materials means if I locate the plant here or here or wherever I locate the plant, would it make any difference to the cost of transportation? In pure materials, the total weight of the inputs is equal to the total weight of the outputs. So it doesn't matter whether I locate the plant at station 1 or at station 2 in terms of the total cost, because the total cost of transportation is going to be the same, isn't it? So when you are dealing with pure materials, where you locate the plant is not governed by the availability of pure materials, but it could be governed by other factors. For instance, it might be convenient to locate the plant at the market itself, because that way you will ensure the minimum transportation of the finished products from the plant to the customer itself. This is of course one reason. This is what happens in all assembly lines. All assembly operations are essentially pure materials. That is, the total weight coming in is equal to the total weight which is going out. And when that happens with pure materials, you don't have any such problem. You can locate the plant anywhere on the line. On the other hand, let us look at weight losing materials. Weight losing materials mean that suppose the total weight of the inputs is 1 ton. The final amount that shows up in the final product is maybe only 10 kg. So you have a lot of materials will lose weight in that sense. Okay. So if you take the same example in this particular situation, what would be the best place to locate the raw material? Obviously the best place to locate the plant would be close to the raw material sources. So we have the raw material sources here, and what you find is, because this will minimize the total cost of transportation. This is the reason why steel plants all over the world are located at the site of the ore, because steel manufacturing is basically using weight losing material. You use lot of ore, lot of limestone, lot of coke, and ultimately the product that you get in weight terms is much less. So it's always preferable to locate the plant at the site of the raw materials. So although here it didn't make any difference, but in weight losing materials it makes all the difference. A third category of raw materials may be what we can call ubiquities. By ubiquities we mean those raw materials which are available with equal ease everywhere. So say typically air and water. So if raw materials are of this nature, where you can get air and water everywhere with equal ease and manufacture this, what would be the optimal decision for locating the plant? Obviously in this case the decision is to locate the plant at the market, because you would minimize the total cost of transfer in that sense. So I think this example should bring home to you that the nature of the raw materials plays a significant role in the optimum location of the manufacturing plant. If there are pure materials, it doesn't matter where you locate, other factors govern. If you are using weight losing materials, it's better to locate at the raw material source. And if you are dealing with ubiquities, then of course it's preferable to locate the plant at the market as far as this particular thing is concerned. So considerations like these are important when you're talking about the location of a plant. So we have talked about the influence of the market, the influence of the raw materials. Similarly, the ease of transportation and transportation cost is a major factor. The availability and dependability of power is an important factor in location. Climate and fuel is an important factor in location. Labor and wages are important. The availability of labor and the wages you pay to them is an important factor. This would be location dependent. Laws and taxation could vary from one site to the other. So these could be factors that might be important for determining the location. Community services could be important when you're trying to find out the best location decision. Water and waste, the availability of water and the capacity to deal with waste products from your plant. This is, and government incentives. Government incentives are, for instance, the government might want to encourage industrialization of a particular state, and therefore it might announce a kind of package of benefits for entrepreneurs. It might say, for instance, that there is zero tax to be paid, or tax holiday for 5 years, or something like that. So those kinds of incentives could also determine where you want to locate if you have these various decisions. Then another important factor that has to be considered is what is going to be the annual cost of operation at a particular site. The annual operational expenses for a plant, which will consist of typically things like the raw materials you consume, the transportation expenses, the real estate expenses, the fuel costs, the sundry state taxes, electric power and water. All these expenses would generally vary from location to location. So if you are trying to compute the annual cost of operation for different sites, you'll have to compare these relative costs and come up with a figure for the annual operating expenses at different sites. Now, very interesting analysis, simple break-even analysis can be done. For instance, if we have two sites, let's say we have site A, location A and location B. Let us say for the time being that location A is a site like Delhi, location B is a site like Mumbai. Now if you compare these two sites, what you find is that Delhi being comparatively less industrialized, it's easier to get, let's say, land in some areas. So the fixed costs are relatively smaller and the unit variable cost is typically higher that is the operational cost will be higher. Why? Because the infrastructure probably is not as strong to supply the raw materials and the various other components of cost. Similarly, in Mumbai, very difficult to get land, very expensive sites, therefore the fixed cost is higher in Mumbai, much higher, but comparatively the unit cost or the annual cost will be lower because a much better infrastructure exists for dealing with these things. So if you now compare this these two, you find that you get a break-even volume of production corresponding to this value. So the decision then is that if your volume of production is lower than this, you should prefer location A, that is Delhi. However, if your volume of production is greater than this particular volume, then you should prefer location B. So this kind of an analysis of fixed and variable costs can compare by taking into consideration the nature of costs at different locations to how you would determine the best location for all possible ranges of operation. Just to give you an idea of a mathematical model which can be used, in fact it's a mechanical analog that we are talking about for finding out the best location of a manufacturing plant. And of course you can solve this problem analytically also, but I think the mechanical analog is very interesting and instructive. This particular model that we are about to discuss is known as Varinon's frame after the inventor. So Frenchman who designed this particular frame for finding out the best location for a manufacturing plant. The model for this particular case is shown here. Suppose we take a table, and on the table we drill holes corresponding to the raw material sources. Suppose there are in general M raw material sources. So R1, R2 and so on up to Rm are the locations of the raw material sources, and we have drilled holes in this particular table here. Then we talk about the markets. This product which we are talking about is going to be produced utilizing the raw materials from these sources, and the markets consist of a number of retailers or people who are going to buy this product. Let's call these markets as M1, M2 and so on up to Mn. So you drill holes corresponding to these locations. Then what we do is we take M plus N strings, धागा ले लीजिए, M plus N strings. When you take the M plus N strings, tie them to a common knot. So from the common knot all the M plus N strings are hanging. Then this is the place of the common knot, and you pass a string through each of these points. You understand? We pass a string through each of these points, and corresponding to each of these M plus N points we hang a weight W1, W2 and so on up to Wm plus N, say. We will just discuss in a minute how these weights are to be calculated, but I think you should appreciate the general nature of this particular model. So having got the weights for this, then you allow the system to come to equilibrium. So assuming that there is no friction on the table, the point where the common knot comes to equilibrium, so this common knot will shift from here to here, right? You can leave it anywhere. Ultimately it will come to a point where the knot is stationary. So that particular point where the knot P comes to equilibrium is the optimum location of the manufacturing plant according to the Varinon's frame. That means you have discovered that this is the best place to set up the manufacturing plant. If you set up the plant here, raw materials are going to flow like this. The assumption is that the flow of raw materials to the plant and all these are Euclidean or straight line. So we assume that raw materials flow like this, and from this point all the product flows in straight lines to the market. So under this set of assumptions, this is actually the optimum point for the location of the manufacturing plant. Here is how we calculate the weight and the assumptions for the model. We have said that in the absence of friction, the common knot P of M plus N strings comes to equilibrium at the least cost location. Basically, what we have done in this model is that we have drawn an analogy. What have we drawn the analogy between? The string comes to equilibrium when the potential energy is minimum. So we have tried to draw an analogy between the potential energy and the travel cost. The system is so designed that there is a analogy between the potential energy and the travel cost. So the moment you say that the potential energy is minimum, it implies that that particular at that particular point the travel cost is also minimum. Okay, this is the. Of course, some of the assumptions are that R1 to Rm are locations of raw material sources, M1 to Mn are location of markets. We are assuming Euclidean or straight line travel, and each weight, how many weights are there? M plus N. There are M plus N in all, and this is how we calculate each weight. Each weight, Wi, is the number of annual trips between P and that point multiplied by the cost per unit distance. Does this make sense? See, you look at this weight. Weight is what we are trying to say is, let's look at the diagram again. Suppose this is a point, a raw material source, and this is the point P, the factory. So what we are trying to say is that the number of annual trips, for instance, if this raw material is to be transported from here to here in trucks, and you expect on the average that there is going to be one truck per month. So in the long run, you are having 12 trucks floating going from R1 to P in a year. Okay, and then you say what is the cost per unit distance, because you don't know this distance. Cost per unit distance is like the rate. So you might say that as far as the truck is concerned, it will cost me something like 15 rupees per kilometer, something like that. If I go in a taxi, I pay maybe 6 rupees per kilometer, whatever it is, right? So there will be a rate associated with the thing. So what we are saying is 12 trucks per annum multiplied with 15 rupees per trip, 15 rupees per kilometer is the cost of this. So 12 into 15 would become the weight that would be relevant for this particular thing. See, the advantage of this particular scheme is that it can take care of different modes of travel. For instance, if the mode from here to here is a train, the travel comes by train. So you know the train is how many rupees per kilometer on the average, multiplied with rupees per kilometer multiplied with the total number of train trips that you are going to make per annum, and so on. If this is going to be manually delivered, then again cost per unit distance of manual movement multiplied with the expected number of trips. So we take into consideration both the mode of travel and the frequency of travel.
So shouldn't you consider the distance of travel?
The distance of travel is automatically taken care of, but we are trying to find out this distance. Basically, that's what the optimization problem is. Ultimately, we say this is this multiplied with this distance and summed up for all these values should be a minimum. So this point comes out such that the total cost of transportation of both raw materials and finished goods is minimized. So this is a model which can actually give us some insights into some of these things. Now, as we said that plant location decisions involve multiple objectives. We had a look at the kinds of factors that are involved. Some of these factors could be subjective, like labor attitudes. Some of these factors could be objective, like costs. Some of the factors could be intangible. Some of the factors could be tangible, right? And many of these factors would be generally measured in incommensurate units, right? For if you're talking about costs, total investment is measured in lakhs of rupees. If you're talking about annual costs, it's measured in rupees per unit time. And then if you're talking about labor attitudes, that's a subjective thing. So you can say cooperative, medium, and restive. That could be one way of classifying these. Now these are all in different units, so you can't add one to the other, and that's what we mean by saying that the factors themselves could be intangible and tangible and could be even incommensurate. So when you are evaluating different factors for plants, you have to consider these considerations and arrive at a possible scheme for evaluation of all the factors. In fact, what we will do in the next lecture is look at a decision matrix approach with proper evaluation of weights of factors and normalization of scores for ranking of alternative locations. And this is done through a case study which we will take up in the next lecture. What we will, however, illustrate at the moment is the use of analytical models for solving the location problem. So what we will consider is a case study of a multi-plant operation and an example of plant addition. So what's happening is, currently, let's say a company has two plants, P1 and P2, located at two geographically distinct locations in the country. So P1 and P2 are the existing plants, and these plants supply to the various warehouses. There are 5 warehouses distributed in the country: A in the north, B in the central region, C in the east, D somewhere close to the west, and E in the south. So these are the warehouses to which these plants actually supply, and these warehouses have the responsibility of distributing the product to the corresponding retailers in their respective regions. But what is generally happening is that the demand for the product has been growing, so that the total production capacity is not able to meet the growing demand for the various warehouses. That is the problem. So the company has felt the need for setting up of a new manufacturing plant, and a site survey has been conducted over the country, and 3 possible locations called X, Y, and Z have been identified where the plant, these are possible locations for the new plant. Basically, we are interested in finding out, as out of these locations, what would be the best location for the company to worry. So this is the statement of the problem for plant location. Basically, the conditions which have triggered this are that owing to the increase of weekly demand to 72,000, there is a capacity deficit of 25,000 per week, and it is felt that a plant of capacity 25,000 could be set up at either X or Y or Z. That's the whole analysis. So the increased demand is here, and now we know that an additional plant with this capacity has to be set up at X, Y, or Z, and all that we are interested in doing at the moment is finding out what would be the optimal decision. And when we consider this decision, we would need data rather than cluttering the entire table with all the data, I would just like you to appreciate that this would be the kind of data that is required, right? So for instance, it is known that the costs of transportation from plant 1 to A, cost of transportation from P2 to A, cost of transportation from the 3 potential sites X, Y and Z to A are estimated here, and the weekly forecast of demand is given. Similarly, all these columns would be estimated, and what you would have is ultimately you will have the capacity corresponding to these plants, which is the existing capacity, and we have already identified that X, Y and Z should have a total capacity of 25,000 to meet the increased demand. And of course you take the unit production costs at the various locations, because costs of production will vary from individual locations, from P1 to P2 to X to Y to Z, because of the various factors like raw material costs and so on, which will vary. So this would be the nature of the problem data that you would be dealing with. So we assume that we have this data, and we'll see how we would carry out the analysis. See, what you have to do is basically look at the problem in terms of, suppose we set up the plant at X, then our possibility would be we'd have an existing plant at 1, plant at 2, plant at X, and our warehouses are these. This is the demand in thousands of units, and the capacity would be 25,000 for X, 27, 20, 27 and 20 here, which are the existing capacities, and the total capacity at an all India level would be 72,000. So what we can do is we can solve this problem. Now in this case we work with only distribution costs here, so we have the costs of distribution. So this is a standard transportation problem which you solve. So when you solve this standard transportation problem, you get the minimum cost of distribution, and that minimum cost of distribution is 26,450, okay, for solving this problem. And then you have to add to this the production costs. The production costs of at P1 of producing so much, at P2 of producing so much, and at X of producing so much. So the total production cost is here, and the total cost for this option, if I set up the plant at X, will obviously be 218,950, which considers both the production costs and the costs of distribution, rather the optimal costs of distribution. Something similar will have to be done for the other two cases, right? You have to again, if we set up the plant at Y, we again have to solve a transportation problem of this nature. Again we get the distribution costs as 26,960. We get the production costs as we get this 193,750, and the total cost is 220,710 in exactly the same manner. And this is the optimal solution, which specifies that of the total production of P2, for instance, 20 units, 10 should be sent to A and 10 should be sent to E. And similarly, the total production of P1, we have 19 should be sent here, so on. And as far as the third one is concerned, we'll have the optimum production distribution solutions continued, and in this particular situation we have, in fact, this should be Z, and we are now talking about the setting up of the plant at the site Z. So again we solve a transportation problem of the same nature, and we get this cost. And it so happens, now you compare the three costs, and it so happens that the total cost of production and distribution is minimum at site Z. This is the minimum, so hence we choose the plant at site Z. Okay. So this was a fairly simple approach to determine where to set up the plant, considering both the costs of production and distribution, and evaluating for each of the options what the total cost is likely to be. Okay. So we have determined this. So this is a case of a plant addition. in that sense of the term. Now, as we indicated earlier, let us carry the case a little further and say, suppose the plant has been set up at site Z, and suppose it is operating for a year or two, and then demands are always dynamic in nature, and let us suppose now that the demand falls. Okay, we are talking about locational dynamics. So we are saying essentially that suppose the third plant is set up at site Z. After some time, demand drops from 72,000 to 56,000 per week. That means we have now planned our plants for a total capacity of 72,000. But there is a fall in demand, and the new demand is now only 56,000 per week. So the question now is not which plant to add, but which plant to shut down, and which plant to run at partial capacity. These are decisions. These are also location decisions. So let's see how we can answer this particular question when the demand drops and we have already 3 plants in operation, 1, 2 and Z, and now we want to find out which particular plant to shut down. Basically, the alternatives before the management are these 4. They can say run all plants at partial capacity. Okay, I mean, you don't produce everything, you produce partial capacity. So we'll find out how much each plant should produce to minimize the cost. Or you have these 3 plants, so you can try to shut down plant 1, and if you shut down plant 2, you might have to use overtime in the other plants to meet the demand. Similarly, you can shut down plant 2 and use overtime in the other plants, or you can shut down plant Z and use overtime in others. So these are the options. So we have essentially 4 options available to us, and what we are going to do is to evaluate these 4 options to find out what is best for the company to do, which particular plant to shut down under these circumstances. So what we are trying to say at this stage is we would need additional data. What kind of data would we need? This is the kind of data that you would require. You know, for instance, that the demand has fallen, so you need to know what is going to be the regional demands of various warehouses. So you estimate that demand for A is 9,000 units, for B it is 13,000 units, for C it is 11,000 units, for D it is 15,000, and E is this. So this exercise would have to be done. It's a forecasting exercise. It's an exercise of estimating what is going to be the demand. So that is what we have done here. Then for the various plants, that is P1, P2 and Z, we would require various costs. For instance, if you run a plant at overtime, it is estimated that the overtime cost of production for the plant, the regular time production costs we already know. So this is the additional data that we are talking about. This is 3.37, 3.33 and 3.27. So overtime production costs could vary. Why could overtime production costs vary? These could vary because wage rates could be different at different locations. Of course, there are other costs pertaining to raw materials, etc., which could also affect these costs. Then you have the overtime capacity. After all, overtime capacity is limited. So we can produce 7,000 here, 5,000 here and 6,000 here at most per week in overtime. Then there are fixed costs. What are these fixed costs? Fixed costs per week, these do not depend upon the production volume. Now if there is a plant already existing, we can think in terms of 2 kinds of fixed costs, while operating and while shut down. So if the plant is operating, then we expect the fixed cost to be 12,000, 9,000, 13,000. If the plant is shut down, the costs won't vanish. all the costs will not vanish. So from 12,000 this can come down to 5,000, because you still have to keep the departments open, you have to keep paying salaries to the various people who are permanent employees of the company and so on. So you have, while shut down, the costs are not zero, but they come down from 12,000 to 5,000, 9,000 to 4,000, 13,000 to 6,000. So if you decide to shut down a plant, these are the fixed costs. If it is operating, these are the costs. I think this is a feature that you have to understand because of the behavior of various types of costs. Now we start to evaluate the 4 options that we were talking about. What was the first option? We were talking about shutdown options. So the first option was basically keep all the plants running, 1, 2 and Z running. So when you keep all the plants running, and you have these are the capacities of the plants, and these are the demands at the various warehouses, you again solve a transportation problem, so you get this kind of solution. You solve this problem and you get a solution. Now take the second option. What is the second option? Second option was we shut down plant 1. So if we shut down plant 1, what happens? Only plant 2 and plant Z are available. Only plant 2 and plant Z are available, 1 is not available. However, you have the possibility of using overtime on 2 and overtime on Z. So the costs that you will take into consideration here will now be the costs of production and distribution. So if you take these costs and solve this problem, you find that the 2Z, 2 on overtime and Z on overtime, the solution is something like this, which means we are talking here only about the optimal solution. And what's going to happen is that plant 2 should produce 20,000 units, plant Z should produce 25,000, 5,000 units overtime on plant 2 and 6,000 units overtime on plant Z, and this will meet the requirements and this will have a certain cost implication. Okay, so this is how you solve this transportation problem. Now in the same manner we can consider the other 2 options. If we shut down plant 2, what will happen? Obviously plant 2 is not available, so the only plants which are available are 1 and Z. You can resort to overtime on 1 and overtime on Z, and you have of course the various warehouses. You can solve this transportation problem again, and you can find out the optimal solution in this manner. Similarly, we can evaluate the situation where we shut down plant 3. If we shut down plant 3, obviously only 1 and Z are available, so we can do overtime on 1, overtime on Z. So our sources are these and our destinations are these. Notice here that when we are talking about A, B, C, D, E and F, F is in fact something which is a dummy warehouse which has been added only to balance the supply and demand. And the solution again obtained for this problem is shown here, where you know how much to ship from 1 to B to C to D, that is 9,000 units, 3,000 units, 15,000 units and so on. And this 3 here shows that as far as the overtime capacity is concerned, you are going to utilize overtime to send items to warehouse B, so on. So I think the point here is that we have looked at the 4 options that are there. Essentially, let us try to recapitulate what we did. We have looked at the 4 options which are there before us. these 4 options in terms of shutting down either a plant. First is don't shut down any plant. So you are running all the 3 at partial capacity. Then shut down plant 1, then shut down plant 2, then shut down plant 3, and you have these various transportation problems which we have solved. So what we try to do is we evaluate these shutdown options, and the significant thing to note here is that corresponding to these 4 options 1, 2, 3 and 4, we find that it is this cost which we have determined by the transportation model, the lower one, and then we can add the fixed cost corresponding to that one as the case may be. I think it's important to realize here as to how we make use of the fixed costs at this stage. You see, in the first option, what is happening? No plant is being shut down, and when you have no plant being shut down, it means all the plants are operating. So the fixed cost is going to be 12 plus 9 plus 13. How much is that? 24. It will be going to be 12 plus 9 21 plus 13 34, and this is the cost 34 here which appears, right? So 34,000 is the fixed cost associated with this option. When you consider option 2, what did we have to do? You have to be careful in selecting the fixed cost. Option 2 was the case where we shut down plant 1 and the others were operating. So let's look at this situation. If plant 1 is shut down, the cost is not this one but just this one. So but the other 2 are operating. So 5,000 plus 9,000 plus 13,000. So that is 14 plus 13, 27,000. So you have a figure here of 27,000. So it has to be selectively done. So what was this option? Let's consider we do it for all these cases, then things would be clear. This was a case when plant 2 is shut down. When plant 2 is shut down, what happens? The cost here is 4,000. Plant 2 has been shut down. So 12,000 plus 4,000, 16,000, 16,000 plus 13,000 is 29,000. So that's the cost, fixed cost here. And similarly, what was option 4? That is shut down plant 3. So if plant 3 means plant Z. So if we shut down plant Z, we find that the total cost is going to be 6,000. So 12,000 plus 9,000 plus 6,000, that is 27,000. So you have the cost here. The point that I am trying to make here is that we have accommodated in the calculation of the fixed costs the nature of the fixed cost under shutdown and under operating conditions, and we have incorporated that here, and these are the values that we have obtained from the optimization in the of the 4 cases. So the total cost is now here, and if you now compare the total cost, we are interested in picking up that option which is the cheapest. So the cheapest option is option number 3, which means it's best to shut down plant 2. You notice an interesting thing here. This is what we mean by locational dynamics. First, when there was a need, we set up a plant at site Z, and then the demand fell and we found that it was best to shut down another plant, not the one that we had set up there. So now we are shutting down plant 2. So if you look at this history, so what we are trying to essentially say is that location decisions are dynamic, and these kinds of decision making has to be done constantly when you are dealing with these various situations. Finally, let's summarize what we have tried to do in this particular lecture. I think the most important thing that we must realize is that location decisions have a strategic importance, because these decisions are there to stay for a long time, they affect the entire organization, and they are costly in that sense. And therefore, there is a need for looking at location decisions more systematically, more scientifically. That was the message. Then we looked at a hierarchy of location problems to suggest that the problem of location is general, and that is why we could term this theory as facility location theory, where the facility would mean that you deal with anything and you are essentially dealing with essentially a location problem. We looked at the Varinon frame, which was an analog model for facility location. It was a very interesting model in terms of strings and weights. Of course, it could be clumsy to use, but you could have a mathematical simulation for this particular model. But nevertheless, it's one of the earliest models used for determining the optimum location. Important factors in plant location were identified. A case study on new plant location and shutdown under dynamic conditions was demonstrated, and we saw how to locate a plant and how to subsequently shut down that particular plant. And of course, based on this analysis, we will do a case study next time of a multi-objective plant location case, which will talk about not only the various factors for location, but also how other facility location models can be used to determine analytically the location problem. Thank you very much.